Hi class, today we're on 2.2 limits involving infinity. In terms of the AP Calculus test, the topics we're focused on is 114 and 115, connecting infinite limits and vertical asymptotes. There's your understanding, objective, and knowledge for that particular topic. And 115, which is connecting limits at infinity and horizontal asymptotes. And there are your understanding, objective, and knowledge. Throughout this section, we're going to focus on all of those. Please remember to make sure you're working on 2.1's worksheets and you're coming in the morning early for help if you're struggling with any of it. Okay, here we go. Limits involving infinity. We are going to look at two kinds of limits involving infinity. We are interested in determining what happens to a function as x approaches infinity, both positive and negative directions. And we are also interested in studying the behavior of a function that approaches infinity in both positive and negative directions as x approaches a given value. Now, what we're going to do here to get started is we're going to investigate this particular function here. This particular function, this would be a rational function and it would have a vertical asymptote at x equals 0. Now, if we wanted to graph that guy, if we remember here correctly from our Algebra 2 or pre-calc days, that would have a vertical asymptote right down the center. If x were -1, my answer would be -1. And this also, believe it or not, would have a horizontal asymptote right there. So if you remember, this is a parent function that you want to be very familiar with. Our graph looks like so. So what we're going to do is we're going to investigate this, but this time we're not going to investigate it as x approaches a specific value. We're going to investigate it as x gets really big or really small. In this case, let's investigate it as x gets really small. And as x gets really small or comes out this way, where does our graph go? And believe it or not, it looks like it's approaching a horizontal asymptote of y equals 0. So we say that that limit's value is 0. Now the limit as x approaches positive infinity of our rational function also goes to a horizontal asymptote of y equals 0. So we say that that limit's value is 0. Let's go ahead and take a look at another rational function. F of x equals 2x minus 1 over x plus 3. Now, if we wanted to graph that guy, same thing, right? We were concerned about rational functions when the function would have horizontal and vertical asymptotes. If you look very closely there, the denominator would be 0 and x equals -3. If I wanted to do just a quick sketch of what this graph looks like, I would put a vertical asymptote right down that line at x is equal to -3. Now, if we remember our rules of horizontal asymptotes, and we'll go over those in a moment, we look at the end behavior model, which would be 2x over x, which I'll get to in our next couple of slides. So there actually is a horizontal asymptote at y equals 2. Now, if I wanted to pick some values to go ahead and graph, you would see that the graph would look something of this sort, okay, which will help us to answer some questions. Okay, what for this particular problem, the limit as x approaches really small values or negative infinity, I'm going to use f of x this time just so I don't have to write down so much. But as we approach x goes to negative infinity, it looks like it goes to the horizontal asymptote of y equals 2. So we say the value is 2. As we inspect the limit as x approaches positive infinity of our function f of x, let's see where that guy goes. That also goes to that horizontal asymptote of y equals 2. So we say its value is 2. Okay, so if you notice something that is very important with these last examples that we've done is this idea of a horizontal asymptote. And so we have a definition. Okay, the line y equals b is a horizontal asymptote of the graph of a function y equals f of x if either as we approach infinity, as x approaches infinity of f of x is equal to that value of b, or, so it doesn't have to be both. Okay, for example, we have a function f of x equals e to the x, exponential function. If you remember what that guy looks like, okay, as we approach here, negative infinity, it goes to 0. So there's a horizontal asymptote at y equals 0 for this particular function. However, as we approach as x goes to infinity from the right-hand side, it grows without bound. So that's why we have that or. Doesn't necessarily have to be the as we go to negative infinity and positive infinity, it has to go to the same value as long as one of them goes to that value. If one of them goes to a specific value b, then we say that there is a horizontal asymptote. Okay, and the question is, can you name parent functions that have horizontal asymptotes? Maybe one, maybe two. And that is your objective, is to be familiar with these parent functions that you've learned in pre-calc and that were on our quiz earlier to start the year. And we want to know what happens to these parent functions as we get really big or we get really small. Now we're going to investigate this, you guys, in a little bit. So we're going to go ahead and skip it right now, and we're going to dive into even more horizontal asymptotes and M behavior models. Okay, so here we go. Let's define M behavior model. Okay, for a rational function. Now, what is a rational function? A rational function is a function that has a polynomial in the numerator and has a polynomial in the denominator. Okay, and it would look something of that sort right there. Okay, and we have M as the degree of what we call it. We'll call M the degree of the numerator. We'll call N the degree of the denominator. And your M behavior model can be written simply as that right there. Now I've got this page right here already filled out for you guys, so I'm going to hit our sweet secret button right here. And I want you to go ahead and hit pause or go ahead and fill out these notes as I talk about them. Okay, you probably remember these from your Algebra 2 days, your pre-calc days. But degrees are, if the degrees of a rational function are equal, let's say n is equal to d, then these guys would end up crossing each other out, and your M behavior model is simply A over B. Now, if you have an behavior model that equals a specific value, then as x approaches positive or negative infinity, we say that y approaches a over b. Thus, there is a horizontal asymptote of y equals a over b. Okay? Now, let's say the larger degree is in the denominator. Now, if the larger degree is in the denominator and we did some math, you get something like that. Okay, now, the idea is if you put a negative or a positive infinity into the bottom, you get a divided by something stupid big. And whenever that happens, y is going to go to 0. So yes, we say there is a horizontal asymptote at y equals 0, and the M behavior model also goes to 0. Now our last situation, what if the larger degree is in the numerator? If the larger degree is in the numerator, we get a result where x would be upstairs. Now this all depends now on whether or not when we subtract n minus d, whether you get an even result or an odd result, right? If we have an even result, we get something that maybe could be parabolic, and both of our M behaviors could go up, or both would go down. But the important thing is they do go in the same direction. If it's odd, they go in different directions. Now we say in these situations, there is no horizontal asymptote because the limit is dne. And if we wanted to inspect it some more, we could do some really fun long division. And situations like this one always have what we call a slant asymptote. And whenever you have anything that has a slant asymptote, finding that actually equation can help us to determine what's happening when x gets really big or x gets really small. Okay, so we have 3 examples here, and I've got some steps to hopefully to get really good at this stuff. Hopefully you remember doing this before. But remember, this works when we have rational functions. And then we'll dive into a little bit what happens if it's not a rational function. Okay, 1, write the M behavior model. Well, how the heck do I do an M behavior model? Well, you take the highest guy upstairs and divide it by the highest guy downstairs. If I go ahead and do that math, I get 2 over 3x. And hey, I should inspect this, or hopefully you have your little table up there, but I think a pretty good way to do this is you put a negative or a positive infinity into that x. And if you put a positive or a negative infinity into that x, you're going to get 2 divided by something stupid big. So where's your y going to go? My y is going to go to 0. Because 2 over something stupid big is definitely going to go to 0. Number 2, evaluate the limit. So how am I supposed to write this so I get 100% on our first quiz in this chapter? We would say the limit as x approaches infinity, because this time it's just infinity, of 2x plus 5 over 3x squared minus 6x plus 1 is equal to 0. Step 3. What does that guy say? Determine whether or not there are any horizontal asymptotes. If so, what is the equation? Well, since the limit goes to 0, guess what? That means there's a horizontal asymptote at y equals 0. And then 4, it says determine if there's a slant asymptote. That obviously doesn't apply to this question. Why couldn't it apply to this question? Well, we just verified that this one has a horizontal asymptote and not a slant asymptote. All right, let's keep this train moving. Step 1. Okay, we'll do B here. Step 1. And you know what a good idea to do, you guys, right now is hit pause. If you think you got a good understanding, hit pause, see if you can do it on your own and see if we end up with the same exact answer. If you do that, you're gonna end up doing really well this year in this course. And behavior model, first step, whenever I'm doing a limit, that is a rational function. And then I divide the highest degree upstairs with the highest degree downstairs. If I do that, bam, those guys cross out. I get an answer of 2. So guess what that means? That means as x approaches, in this case, we're just worried about the infinity case. So as x approaches infinity, where does y go? Y is going to go to 0. So guess what? Let's just write this all pretty nice. And we're going to write the limit as x approaches infinity of 2x squared minus 3x plus 5 all over x squared plus 1. And what does that equal? That equals 0. Step 3. Well, hey, ooh, equals 0. What am I doing? 2. So y goes to 2. That means the limit is equal to 2, right, class? Whew. Good thing you tried this on your own first. 3. Determine whether or not there are any horizontal asymptotes. Well, since the limit goes to a value, then yes, we know that there's a horizontal asymptote at y equals 2. All right, here's our last one, which is going to be the most fun one because we get to show off some serious math skills. All right, here we go. Step 1, our EBM or our end behavior model. What do? We divide the first guy upstairs with the first guy downstairs. And when I say first, it does have to be the leading term, right? So the highest exponent. If I go ahead and do that division, I get, believe it or not, a x over 3. If I get an x over 3 and this one says as x approaches infinity, well, as x approaches infinity, so if my x values get really, really big on the positive side, guess where y is going to go? It's going to go to infinity. Well, what the heck do we say in terms of a limit in that situation? Well, step 2, the limit as x approaches infinity of x squared plus x plus 9 over 3x minus 3. We say that does not exist. And it's very important to say because as x goes to infinity, our function, we like to say, grows without bound. And sometimes we ask, hey, does it grow positively without bound or negatively? This one, because when I put positive values in there, I get like 1,000,000 over 3, 1,000,000,000,000 over 3. That thing's growing to the positive case without bound. Whew, step 3. Step 3 says to find a horizontal asymptote. Well, hopefully we learned from those notes we took above that there's no horizontal asymptote. Well, if a rational function does not have a horizontal asymptote, what does that mean? That means step 4, there is a SA or a slant asymptote. So the question is, how the heck do we find a slant asymptote? Well, we do this really fun long division stuff, okay, which whatever's on the bottom we put here on the outside. Whatever's on top goes underneath this roof. Okay, and I'll give you some techniques in case you forgot long division, but you've been doing it probably since the 4th or 5th grade, I would want to say. But I start kind of in cycles with this, okay? Step 1, you divide the first guy underneath the roof with the first guy outside. Okay, and if you go ahead and you do that division, we get 1/3 x. Okay, and I stack that guy up here. That's my first answer. Okay, that's going to be in my slant asymptote, which is 1/3 x. And I'm going to stack it above the x. And then after we do that, we do a little multiplication. We multiply that 1/3 right here by both of those guys out here. Okay, and I kind of just keep a process going. Okay, and if I multiply by both those, I get x squared minus x. And if that first guy does not match up, it means you did it wrong. Now, the most important thing in long division, after I do that, I have to subtract that term. And if I subtract that term, that is going to be my first remainder. 2x. Those first guys, if you notice, they cancel out. If they don't cancel out, then that's a great indicator that you made a mistake. Now, after I write my remainder down, I just say, hey, can I keep on going? And you can keep on going as long as the first guy underneath the roof, which is now 2x, okay, as long as that degree is bigger than or equal to the degree of that guy. So as long as I can still do some math like that, I'm going to keep on getting answers. Okay, my second answer is 2/3. Okay, where does that guy go? That guy goes above the 9, so there's 2/3. Okay, what's my next step after that? I multiply. It's a nice little process we got going on, right? And if I multiply this, I get 2x minus 2. Okay, what do I do after that? This is what most students forget. I subtract that entire term. And if I subtract that entire term, I get a remainder of 11. Now, if you look, that is x to the 0. That degree is smaller than the degree of that guy out there. So that means I'm done. This is my remainder. Now, how do we write remainders in AP Calculus? Well, my answer for this is the slant asymptote is y equals 1/3 x plus 2/3 plus 11 over 3x minus 3. And believe it or not, in slant asymptotes, we don't care about that guy. Do you know why? Because if we care about we observe slant asymptotes when x gets really big or really small. Now, when x gets really big or really small, this guy's going to go to 0 every single time because it's 11 over something stupid big. So that is my slant asymptote, and it's as easy as this, class. Does this here have a positive or negative slope? It's got a positive slope. So that tells me a lot about what's happening as x goes to infinity. So as x gets big, where do we go? Positive infinity. Guess what? If this question asked if x goes to negative infinity, where does it go? It goes actually to negative. Y goes to negative infinity. But it doesn't matter. The answer that we use for both of these, whether we're going to positive or negative infinity in terms of the y value, is we just say it's d and e. Why? Because the function grows without bound. Now, the interesting thing to note here is as x goes to infinity, or if x goes to negative infinity, if they are equal to each other, okay, we say there's going to be a horizontal asymptote. And when does this happen? With rational functions. A general rule for functions that are divided, not necessarily rational functions, is 1, if the denominator grows faster than the numerator, the limit as x approaches infinity will be 0. 2, if the number grows faster, if the numerator grows faster than the denominator, then as x approaches infinity, the limit will not exist. 3, if the numerator and denominator grow at the same rate, look for a limit of a non-zero constant. Now, last section, remember, we had this awesome cheat we get to use for the rest of the year. Whenever it comes up, we can just assume that, right? Never supposed to assume anything, but you can assume that. But what the heck happens to that same function as x gets really, really big or x gets really, really small? Remember from last time, if I inspect really close, we got that. But you know what's super cool? Put that bad boy in your calculator and something really interesting happens. And it kind of works like that. Kind of cool, right? And what it is it kind of jumps between -1 and +1 there. But as x gets really, really big or x gets really, really small, where does it go, class? It goes to 0. And if x gets really, really big or really, really small and it goes to 0, we say that it has a horizontal asymptote, right, class? And what's the horizontal asymptote? Y equals 0. So even though this particular function is not a rational function, why is it not a rational function? Because it's not a polynomial upstairs. It's polynomial downstairs, but to be a rational function, it's got to be a polynomial upstairs and downstairs. This guy is not because of that trig function up there. It could still have a horizontal asymptote, and this is a case where that does happen. All right, here we go. Let's look at something that's just a little bit different and that you just have to be really good to be able to figure out, okay? And to figure that guy out, we are going to look at the limits as x approaches 0 from the right and as x approaches 0 from the left. I just lied. Shame on me. I've got another one in my notes that are not in your notes. Okay, so what I want you to do is pull out a separate sheet of paper because this dude is really important and it's not on this one here, but it's in my notes. So let's go ahead. I'm going to get a blank page up here. Okay, so here's my blank page. Okay, so make sure you guys have a blank page yourselves, okay, because you need this very important problem. It's going to come up in your notes. Let's inspect the limit. as x approaches infinity of 5 plus 2 to the x all over 3 minus 2 to the x. Now, this is an example that if I were to put in a positive infinity, the numerator and denominator are going to grow at the same rate. And believe it or not, I know it's a little weird, but the best way to do these types of problems that are different, that are not rational functions, and we can't really inspect end behaviors, is we're going to get a little weird and we're just going to substitute an infinity. It seems like a little crazy, but you have to do this to be able to get this. And these come up a lot as multiple choice questions on the actual AP exam. Okay, but that's like 2 billion, trillion, million, trillion, plus 5. That is like 2 million, billion, trillion, plus 3. Okay, but the negative case. And if you look, they grow at the same exact rate. So as x gets ridiculously stupid big, believe it or not, it looks like the top and the bottom are going to equal about the same exact thing, except one's positive and one's negative. Well, what would my answer be in that case? Negative 1. So believe it or not, for this particular function, which is dealing with some exponentials in the numerator and the denominator, as x gets really big, as x approaches infinity, our function goes to negative 1. Now, you're probably saying to yourself, Mr. Tanaka, that's not too bad. Okay, check this bad boy out. And if you really want to be challenged, I challenge you to hit pause, direct sub a negative infinity into the same exact function, and see if you can figure out, without my help, what this guy goes to. Okay, so go ahead and pause. But I'm going to go ahead and keep going right now. If you don't want to be challenged, shame on you. 5 plus 2 to the negative infinity. What? Over 3 minus 2 to the negative infinity. What? Well, I better do some simplification first, because a negative exponent, for me, I don't like negative exponents. So since I don't like negative exponents, I always rewrite those bad boys. That means it's really 1 over 2 to the infinity, all over 3 minus 1 over 2 to the infinity, right? That's exactly what that bad boy means. And guess what? As x gets really, really big, right? As that gets really, really big, the numerator's 1. The denominator of that is something stupid big. So that means this piece right here goes to what, class? It goes to 0. This piece right here, same exact thing happens. Where does that go? That goes to 0. Well, what's 5 plus 0? 5. What's 3 minus 0? 3. So guess what? The limit of that function, believe it or not, is 5/3, which is crazy. Get out that bad boy TI-84 calculator, graph this function, and it's kind of cool. There are 2 horizontal asymptotes. One of them is negative 1, that says x gets really, really big, and another one is 5/3 as x gets really, really small. Kind of cool how that one works out. Okay, we've been dealing a lot with horizontal asymptotes. Now, how do vertical asymptotes come into play, right? It's getting a little, vertical asymptotes getting a little jealous here. So let's talk about these guys. And these guys end up happening as we approach a specific value A. For example, let's go back to this function that we kind of started this lesson with, which is 1 over x. Okay, hopefully we all know that it looks like by now. Has a vertical and a horizontal asymptote. But what we're going to do is we're going to inspect what happens as we approach 0 from the right. Okay, so what happens as we approach 0 from the right? Well, as I approach 0 from the right-hand side, what's happening to my y value? It gets crazy big, infinity. More important than that, the way we like to answer these questions is just with a DNE. Why? Because we like to say the function grows without bound. Okay, and we can go without bound. Okay, and it grows positively, we would say without bound. Now, let's go ahead and look at this limit as x approaches 0 from the left-hand side of 1 over x. Okay, let's check this from the left-hand side would be coming from this. Whoa, that equals negative infinity. That's just being super specific. The better answer is, why? Because remember, if we go back to our definition of a limit, it's got to go to a specific value, okay, for the limit to exist. So we say these do not exist, same answer, because the function grows without bound. If I wanted to be specific, I could say it grows without bound negatively. Okay, kind of, let's get to a formal definition. The line x equal a is a vertical asymptote of a graph, okay, of a function y equals f of x if either of these 2 situations occur. Okay, infinity is not a number. You need to remember that, and thus that's why the limit fails. We just talked about that. Okay? Okay, last example of the day. they're asking me to look at this function f of x equals 6x minus 3x squared all over x squared minus 4. And they're asking me to do it without a calculator. Well, that means it's a fun problem. How do I do this without a calculator? Well, it's a rational function, and what's the one thing we are concerned with rational functions? A good way to start is always with your horizontal and your vertical asymptotes. Well, horizontal asymptotes, right, class, is what? M behavior model. What's my M behavior model? My M behavior model is the highest degree on the top term with the highest degree on the bottom, and that means that would equal -3. So I have a horizontal asymptote at y equals -3. Okay? Now let's go ahead and find a vertical asymptote. Why do I find a vertical asymptote? But usually you set the bottom equal to 0, but you always have to be careful. Because just because the bottom is equal to 0 for a specific value, we may have what we call, remember, a removable discontinuity. So the first thing we're going to do is we are going to factor. Okay, I could take a 3x out of the top. If I take a 3x out of the top, I am left with a 2 minus an x, right? If I factor the bottom, that's a difference of squares. I get x plus 2x minus 2, okay? Now, a lot of students make this mistake, so let's be very careful here. Okay, it looks like I can almost cross these guys out, but they're a little bit different. Well, I could take a negative out of that. Okay, if I take a negative out of that, I get exactly the same thing on the top and on the bottom, which means I can cross those out, which means there is a removable. It's a discontinuity, but it's a removable discontinuity. Now, why is that very important in this problem? Because I only have one vertical asymptote, and it happens at when x is -2. So even though a positive 2 does actually make the denominator equal to 0, it's not a vertical asymptote. Why is it not a vertical asymptote? Because I was able to remove it, thus the term removable discontinuity. Now, I'm able to answer the question, which is what's happening from the left and to the right-hand side of our asymptote, it's going to be important to know what this graph looks like. Well, I have a vertical asymptote we just figured out at x equals -2. I have a horizontal asymptote at y equals -3. And I can just do a real quick sketch here to give me a real brief understanding. Now, I really just need another point to get a graph. Okay, so let's go ahead and choose, I'm going to choose 1, then I'm going to choose -3. And if I put a -3 in there into my simplified function, I'm going to get a negative answer. So that, believe it or not, means the graph is there. Okay, let's put a number. So it's going to pick a number to the left and a number to the right. Let's pick a number to the right, like -1. If you put a -1 into that function, you get a positive. Okay, so just a real brief sketch gives me a graph that looks like that. And now I can answer my questions, right? I can answer my questions for this. Sorry, guys. And that is, we wanted to find the limits in the or the function's behavior as we approach from the left and the right-hand side. And we would like to write these as limits. So let's go the limit as x approaches, let's see, where was it? It was -2. And let's go the left-hand side first. And I can either write out that entire function, or I could just write f of x. Why? Because they were defined that they were equal to one another. And as we approach 2 from the left-hand side, my answer is -infinity. Or you know what? Let's be safe, and let's just put dne. Why? Because it grows without bound. Okay, now let's look as we approach -2 from the right-hand side. Once again, let's just put f of x. Why? Because I'm allowed to, because they are equal to each other. And same thing, even though from the right-hand side it goes to positive infinity, let's just write dne. That's a good blanket statement. That's the better answer. And why do we say it's dne? Well, it grows without bound. That's section 2.2. Let me give you a brief look here. I hope you guys enjoyed it. It took a little bit of time. I'm trying to keep every single one of these under 30 minutes because I need you working on those worksheets. Challenge yourself. Get better. Come in early for help. If anything didn't make sense today, I'm more than happy to work through anything with you. Aloha.